There is also heat energy. And heat energy is expressed in a very different way. We express that in terms of calories. And a calorie is defined in a very special way as the energy which is needed to increase 1 gram of water by 1 degree centigrade. And so in general we can write that Q, which is heat energy, which is in calories, is the mass of the object times the specific heat, which for water would be 1 calorie per gram per degree centigrade, times the temperature increase that we apply. So we increase the temperature of an object. The object has a mass m. We increase the temperature by this much, so many degrees Kelvin or degrees centigrade, that's the same. And then this is the number of calories that you have to put in there. I gave you the specific heat for water in calories per gram, not per kilogram. If I gave it per kilogram, which may be nicer for this course, then of course it would be 1,000 instead of 1. Aluminum has a specific heat of 0.2. Lead is unusually low, is only 0.03. It's a very, very low. Ice is only half the specific heat of water. Ice is only 1/2 calorie per gram per degree centigrade. The physicist James Joule, after we call after him the unit of work, was the first to demonstrate that heat energy and mechanical energy are really equivalent. He did an ingenious experiment. Of course, once you hear it, you said, well, I could have thought of it myself. He takes objects with masses which hang from strings, and he lowers them in a gravitational field over a certain distance. So he knows what mgh is. And he uses these rope to rotate scoops, which are in water. And these scoops are driven, that is mechanical energy, mgh comes out in the scoops, and what does he notice? That the temperature of the water goes up, and he measures the increase in temperature, and he knows how the calorie was defined, and so he found that 1 calorie is approximately 4.2. Now it's called joules. At that time it wasn't called joules yet. So there is a direct connection between the two. I would like to, I'm going to throw several numbers at you during this lecture, and I prepared a view graph. Don't copy the numbers because it's all on the web, but some of these numbers I will return to, and therefore I thought I might as well compile them in one. You see there on the top there that 1 calorie is 4.2 joules, and you also see the horsepower and other units that will come up very shortly. I all defined there. When we burn something, there is a chemical reaction which produces heat in many cases. Gasoline produces per gallon something like close to 100 million joules. Your body produces heat. Your body is roughly at a temperature of 98 degrees Fahrenheit, unless you happen to run a high fever today. And your body is radiating electromagnetic radiation. You can't see it with your eyes because it's infrared. But when it's dark and you hold someone in your arms, you can feel that heat. That heat is a fantastic amount. That is about 100 joules per second that you radiate. 100 watts. You radiate at the same level as a 100-watt light bulb, but it's, of course, distributed over a much larger area, so you're not that hot as a 100-watt light bulb. But it's a fantastic amount. 100 watts that you radiate for the simple fact that your body has to be kept at that temperature. It means that it is in one day about 10 to the 7 joules that you generate. 10 to the 7 joules. That is what you generate in terms of heat. 10 to the 7 joules per day. And that is about 2 million calories per day. Where does the body get it from? Food. You better eat 2 million calories per day. Now I can see some of you turn pale and green and purple and say, over my dead body, 2 million calories per day, you must be out of your mind. Well, not quite. You see, when you read on the packages calories, then it is called a capital CAL, and that is really a kilocalorie. So you have to divide this by thousands to compare it with the packages that you buy, how many calories there is in the food. So you have to eat roughly daily about 2,000 kilocalories equivalent of food. And if you eat a lot more than that, well, you pay a price for that sooner or later. How about mechanical work? Don't we have to eat also for all the mechanical work that we do? We work so hard, and I'm sure there must be a lot of energy going into that work. Well, I have a surprise for you. It's very disappointing. The kind of work that you and I do in one day is so embarrassingly little in terms of mechanical work that you can completely neglect it. Suppose we go up 3 floors. We walk up 3 floors, which is about 10 meters high. And let's say we do that 3 times per day. And let's give you a mass of about 70 kilograms. It's about my mass. How much work do I do when I do that 3 times? Oh, let me do it 5 times per day. Boy, I really go out of my way. 5 times per day I go 3 floors up. Well, the amount of work that I do is MGH. MGH. The 10 meters have to be multiplied by 5 because I do it 5 times. And so I get 35,000 joules of work that I do. 35,000 joules. Compare that with the 10 to the 7 joules per day that your body generates in terms of heat. You think you have to eat a little bit more for these lousy 35,000 joules? Forget it, it's nothing. In fact, your average power, if you walked up these stairs and you spread it out over a day, and say it took you 10 hours. You go once up in the morning and then sometime in the afternoon, and you go up in the evening and maybe twice in the evening. It takes you 10 hours to go 5 times up these 3 floors. Then the average power that you have done, that you have generated, is 35,000 joules divided by 36,000 seconds. That is embarrassingly little. That's about 1 watt. Compare that with your body, which generates 100 joules per second every second, 100 watts. So it is completely negligible. However, if you climb a mountain, 5,000 feet, and you do that, then the work you have to do is 1,000,000 joules. Now 1,000,000 is no longer negligible compared to the 10 to the 7. And so now you feel hungry, and now you really need more food. And if you do that in 2 hours, the power that you have generated is substantial. You would have generated an average power of 160 watts, more than the body heat, during those 2 hours, of course. And so now the body says, I want to eat more. I want to be compensated for the work. If I climb this mountain, if I climb 5,000 feet, and I have to do an extra work, which is 10 to the 6 joules, you got to eat more. Now, you would think that you have to eat only 10% more than you normally eat, because you say 10 to the 6 is only 10% of 10 to the 7. But that's not true. You have to eat a lot more, because the conversion from food to mechanical work is very poor, something like 20%. So you may have to eat 40 or 50% more than you normally do in one day. Suppose I wanted to take a bath, and I want to calculate how much energy it takes to heat a bath. A wonderful thing to have. Well, we now know how to do that. Q is the number of calories. M times C times delta T, that's the equation. A bath would contain about 100 kilograms of water. That is about 28 gallons. And let us assume that the temperature increase is about 50 degrees centigrade, which is the same as 50 degrees Kelvin. We have water, and so you'll find that Q then becomes roughly 5,000 kilocalories. That's how much heat energy it takes which is 2 times 10 to the 7 joules. So that's the energy that is needed to heat up a bath and enjoy that pleasure. I'll get back to this bath very shortly. There are many forms of energy, as we're all familiar with. There is electric energy, there's chemical energy, I mentioned that already, gasoline burning, there is mechanical energy when we move things, gravitational field, and there is nuclear energy. A waterfall is mechanical energy, MGH. You can convert that to electricity. You can convert it to heat. Electricity will power your coffee machine. It will power your TV, your radio, your VCR, your electric toothbrush, everything. It may power your electric blanket if you have one. Electric blanket is only 50 watts. Compare that with a human being. 100 watts. Much nicer to have a human being with you in bed than one electric blanket, believe me. Nuclear energy can be converted into heat. And that can be converted into mechanical energy. And again into electricity. Chemical energy. Gasoline, fossil fuel, can be burned, converted to heat, converted to electricity. I have here a device that allows me to convert mechanical energy to electric energy. And I would like to invite a student to come up here, a volunteer, he or a she, who is going to show how he or she can convert mechanical energy into electric energy. We'll have the special light conditions so that we can see it well. So who wants to do that? Yeah, please come. There is a 20-watt light bulb here. You will see it very shortly. And this man has a lot of power, I can tell. More than 100 watts. Go ahead. Power that 20-watt light bulb. Put your foot on here. Take it easy. Quite impressive, eh? Okay, now we'll tighten the nuts a little on you. Here we have 6 of them. So now, go ahead, and now you are trying to generate 120 watts of power. You think you can do it?
Try.
Try it. They look pretty dim to me. Nowhere near. Nowhere near. Keep going, man. Keep going. You're not even at the level of 120 watts. It's hopeless. It's hopeless. You can't do it. And even if you could do it, you would have to do this for 48 hours in a row to heat up my bathtub. Think about that. For one bath, 48 hours. But you can't even do it. 120 watts is too much. I don't blame you. I can't do it either.